Hello everyone. In this video, we'll be seeing linear partial differential equation of homogeneous types. First, let me define what is a linear PDE of homogeneous type. Already we have seen how to name a PDE as a homogeneous PDE. So the definition of homogeneous PDE is that is every term must contain either dependent variable or its derivatives. However, when we see about PDE of homogeneous type, this is the definition. All the terms should have the same order of differentiation. That is, if we define an nth order PDE, or for example, I am taking n is equal to 2 and I am going to define a PDE of second order homogeneous type. So every term must have second order derivative. So for example, dou square z by dou x square plus dou square z by dou x dou y plus dou square z by dou y square equal to 0. You see that in all the terms I am having the order of derivative as 2. Since all the terms have the same derivative, we can say this PDE is of homogeneous type and it is of second order. So in this one, it is not necessary that this right hand side should always be 0. Instead, here we can have this one as a function of x comma y. So from this definition itself, we can understand there is no relation between homogeneous PDE and PDE of homogeneous type. Because in the homogeneous PDE, always our right hand side, that is right hand side term should be 0. If we bring all the dependent variable and its derivative terms to left hand side, the remaining part in our right hand side should be 0. But here the right hand side can be any function of x comma y. So there is no dependence between these two things. If we have different order derivatives in a single equation, then it is called as a PDE of non-homogeneous type. So this is the general nth order homogeneous type I have written here, and this has constant coefficients. For example, this A0, this A1, this AN are all constant coefficients. Observe that here we have taken nth order derivative throughout the equation, and the right hand side it may be any function of x comma y. So this is a general form of linear PDE of nth order homogeneous type. Okay. Now we are going to represent this equation in a short form. I am going to name d as dou by dou x and d dash as dou by dou y. So in this equation, so this can be dou power dou n z by dou x power n. This can be represented as capital D power n, and here we are having n minus 1th order derivative of x. So it can be written as d power n minus 1, and first order derivative of y, it is g, etc. Here it can be replaced as d dash n. So the same thing we have written here, and then this term, the term in our left hand side, it can be written as some function of d comma d dash. So now if we take the left hand side alone and find the solution, that solution is called as complementary function of the given equation. And finding the solution when our right hand side is not equal to 0, that is called as particular integral, and the general form to find the particular integral is pi, that is particular integral is nothing but right hand side divided by the function f of d comma d dash. And always we have to write a complete solution for a given equation. So this part it is important. complete solution, it can be written as CF, that is complementary function plus particular integral PI. So for a given question, we have to find complementary function and particular integral we have to find whenever the right hand side is not equal to 0. Now how to find the complementary function? We are going to replace capital D with M and capital D dash with 1. So we'll get an equation in terms of M. Now if we find the roots of this equation, that using that roots we can write the complementary function. So since this is an nth order equation, will be having n roots. So based on the characteristic of that roots, we can write the solution. If all the roots are real, so here no need to differentiate between real and complex number. Either it is real or complex. If they are distinct, we can straight away write it as function f1 of y plus m1x plus f2 of y2 plus m2x plus fn of y plus mnx. And similarly, when two roots are equal, for example, without loss of generality, I am going to take first two roots are equal. In that case, how to write the solution? We are going to replace m1 with m, m2 with m, and in second part, we have to multiply with x. After that, these are all distinct roots, so we can write similar to case 1. So next one, when three roots are equal, without loss of generality, we are taking first three roots are equal. So in this case, up to x square term we have to extend and all the roots will be same for first three parts. So let us solve this equation. Solve d square minus 5d d dash plus 6d dash square into z equal to 0. So first we have to write the auxiliary equation. Writing auxiliary equation is nothing but replacing capital D term with m and capital D dash term with 1. So if I replace the first term with m, I'll get m square. And second term d with m will get this one. D dash into 1 will be the same thing. So if I put d dash as 1, 1 square will be 1. So it is plus 6. Now if we factorize this equation, we will get, so it is m minus 2 into m plus 3. This is equal to 0. So now our roots are m is equal to 2 comma 3. These are the roots. Now how to write the complementary function? Since these roots are distinct, we have to go for case 1. So it is f1 of y plus m1. Here the first root is 2. So it will be 2x plus f2 of y plus second root. It is 3x. So this is our complementary function. So now to write the complete solution, since there is no right hand side term in this question, the particular integral does not exist. So we can write the complete solution as complementary function itself. So our solution will be z equal to f1 of y plus 2x plus f2 of y plus 3x. So now let us go to next problem. So d cube minus 4d square d dash plus 4d d dash square into z equal to 0. Here writing complementary function is not, auxiliary equation is nothing but replacing d with m and d dash with 1. So first term it will come as m cube. Second term it will be 4m square into 1. We can write it as 4m square plus 4m into z equal to 0. So our auxiliary equation is nothing but writing m cube minus 4m square plus 4m is equal to 0. Now we have to find the roots of this equation. Since all the term contains m, we can take m outside. It will be m square minus 4m plus 4 is equal to 0. We can see that this is the equation m minus 2 the whole square. M into m minus 2 the whole square equal to 0. We can write m values as 0. If we equate m minus 2 to 0, we will get 2 terms. So the roots of this equation are m is equal to 0 to 2. observe that the first root is distinct but the next two roots are repeated. So to write the complementary function, we have to write the first root as it is. So we will be writing f1 of y plus 0x and then f2 first in the repeated root we are writing the first term. So we can write it as it is, and since we are writing the second term we have to multiply that with x into f3 of y plus 2x. So this is our complementary function. This first term it can be replaced with f1 of y. Since 0 into x is 0, y plus 0x will be y. This is our complementary function and there is no particular integral for this question. So the solution is simply the complementary function itself. So now to find the particular integral for some standard types or specific right hand side terms. So let us take the first type f of x comma y is equal to e power ax plus by, and second type is sin ax plus by cos ax plus by, and third one powers raised for x and y terms. So x power m into y power n, and type 4 is nothing but e power ax plus by multiplied with either type 2 problem or type 3 problem, and type 5 is nothing but f of x comma y. It can be any function. So now in this lecture we shall see how to do the or find the particular integral for type 1, that is e power ax plus by. So I'll give the general method. If f of x comma y is equal to e power ax plus by, then already we know that the particular integral formula is nothing but f of x comma y divided by f of d comma d dash. In this type, f of x comma y is nothing but e power ax plus by. So here remember that for type 1 we are going to replace d with a and d dash with b. These a and b terms are nothing but the coefficients of x and y in exponential term. So if after substituting d as a and d dash as b, the denominator it doesn't becomes 0, we can fix this one as our particular integral. Suppose if we get the denominator as 0, then again we have to differentiate this denominator once again. That is f of d comma d dash, we have to differentiate it once and then we are going to multiply pi with x. So this derivative we are going to find it with respect to d, not with respect to d dash. So if we are differentiating with respect to d, d dash will act as a constant. Then we can substitute a comma b similar to previous case. If we again get the denominator as non-zero value, we can stop there itself, or if it comes as 0 value, then we have to proceed with the next term, multiplying with x square, writing double derivative in denominator, substituting d equal to a and d dash is equal to d. So let us solve some problems in type 1. We are having d square minus 2d d dash plus d dash square into z equal to e power x plus 2y. So first always for a given problem we have to find complementary function, and then if the particular integral exists we have to find it. So here auxiliary equation is replacing d with m and d dash with 1. We will get the auxiliary equation m square minus 2m plus 1 is equal to 0. So this can be written as m minus 1 the whole square is equal to 0. So our roots will be m is equal to 1 comma 1. Since these roots are repeated, first term we can write as it is. It will be y plus 1 into x, we can write it as x, and for second term which is a repeated root we have to multiply with x. So x into f2 of y plus x. This is our complementary function. So after finding complementary function, next we have to find particular integral. So already I have told you the formula for particular integral is nothing but 1 by f of g comma d dash e power x plus 2y. So since f of x comma y in this problem is e power x plus 2y, this is equal to, we can write the term given in the question, which is d square minus 2d dash plus d dash square e power x plus 2y. Now we are going to put d as a and d dash as b. This is equal, so this is equal to 1 by, so if we put d as a term it is nothing but 1 because the coefficient of x is 1 in the function and b is 2. So 1 square will get 1 minus 2 into d is 1, d dash is 2. So 2 into 1 into 2 will get minus 4 plus d dash is 2. If we multiply that, we'll get 4 e power x plus 2y. Now this minus 4 and plus 4 will get cancelled. 1 by 1 value, denominator it becomes non-zero. So we can fix 1 by 1 as 1. This is equal to e power x plus 2y. So our particular integral for this question is e power x plus 2y. Writing complete solution, it is nothing but z equal to cf plus pi. Just combining both the terms. This is our cf and this is our pi. I hope this problem is clear. Let us go to next problem. D plus d dash square into z equal to e power x minus y. So auxiliary equation we'll get it as m plus 1 the whole square equal to 0. Roots will be minus 1 and 1, and then our complementary function is f1 of y minus x plus x into f2 of y minus x. So I'll find particular integral. So particular integral is 1 by d plus d dash square into e power x minus y. So we can expand this one in form of a plus b the whole square. It will be a square plus 2ab plus b square into e power x minus y. So we replace d with a and d dash with b. A value is nothing but 1 and b value is minus 1 in this question. So this is equal to 1 divided by 1 plus 2 into this value is 1 into this value is minus 4. So it will get minus 2 plus d dash square minus 1 the whole square value is 1 e power x minus y. This is equal to 1 by 1 minus 2 plus 1 into e power x minus y. This will be equal to 1 by 0 e power x minus y. So since we are getting 0 in our denominator, next we have to go for derivative. So pi, it can be written as x into 1 by derivative of this part with respect to d. So we'll get 2d plus d dash will act as a constant. If we differentiate with respect to d, we'll get the constant term alone, 2d dash into this d dash constant derivative will be 0 e power x minus y. So this is equal to x by 2 into d is 1 plus 2 into d dash is minus 1 e power x minus y. This is equal to x divided by 2 minus 2 e power x minus y. So we'll get x by 0 e power x minus y. So again we are getting 0 in denominator. So we have to go for next part. So pi it will be x square 1 by, we have to differentiate this part with respect to d. So it will be 2 plus 0 e power x minus y. Since there is no d and d dash term as denominator, we can write it as it is x square by 2 e power x minus y. So this will be our particular integral. Now to write the complete solution, it will be complementary function plus particular integral. We'll get this answer. So next one, d power 4 minus d dash power 4 into z equal to e power x plus y. So this is our auxiliary equation, m power 4 minus 1. We can see that as m square the whole square minus 1 square equal to 1. A square minus b square. It will be a plus b into a minus b. So the roots will be 1, minus 1, I and minus I. This is the complementary function. Now to find particular integral, we can keep the term as it is, and 1 by d will be replaced with a, that is 1. D dash will be replaced with b, that is 1. So 1 minus 1 will get 0 in the denominator. Next we have to differentiate this term. So pi, it can be written as x into 1 by, if we differentiate d power 4, we'll get 4 d cube minus this d dash is constant, so it will be 0 into e power x plus y. So this is equal to x by 4 d cube e power x plus y, which is equal to, we can write d as 1, so it will be x by 4 e power x plus y. This is the particular integral. So our complete solution is CF plus BI. So in this question, e power x into cos hy is given. We already know that the formula for cos h is nothing but e power x plus e power minus x divided by 2. So same manner, we are going to replace x with y. So cos hy will be e power y plus e power minus y by 2. We are going to replace that in this question. So auxiliary function is m square plus 3m plus 2 equal to 0. You can write it as m plus 1 into m plus 2 equal to 0. So m can be written as minus 1 comma minus 2. So the complementary function will be f1 of y minus x plus f2 of y minus 2x. Now to find the particular integral, it is given that 1 by d square plus 3 d dash plus 2 d dash square into e power x cos hy. So we can write this part as 1 by d square plus 3 d dash plus 2 d dash square e power x into cos hy is nothing but e power y plus e power minus y divided by 2. Since 1 by y is a constant, I am going to take it as outside. 1 by 2 is a constant. And then 1 by, we can write d square plus 3 d dash plus 2 d dash square into e power x plus y plus e power x minus y. So now we can multiply this term separately inside the bracket. It is 1 by d square plus 3 d dash plus d dash square into e power x plus y plus 1 by d square plus 3 d dash plus d dash square e power x minus y. If we substitute the term a and b, there are two parts. For the first part, a and b is 1. For the second part, a is 1, b is minus 1. Correspondingly, we can substitute it. 1 by 1 plus 3 plus 1 e power x plus y. And then here it is plus 1 by 1 plus 3, or this is minus 3 d dash square will be minus plus e power x minus y. So this is 2d dash. Yes, 2, 2. So here it will be 2. Here it will be plus 2. So we'll get equal to 1 by 2 into 1 by 6 e power x plus y plus 1 by 0 e power x minus y. Since we get 0 in denominator, next step we have to go for 1 by 2 into first term we can keep it as it is because the denominator is non-zero. For second one we can write it as x by derivative of denominator, it is 2d plus 3d dash into e power x minus y. So now if we substitute it here, it will be 1 by 2, 1 by 6 e power x plus y. So if we put ds1 and d dash as minus 1, we'll get minus x by 4 e power x minus y. So this is our particular integral. Minus x e power x minus y. So the solution is complementary function plus particular integral.